Whoops. What? Okay, guys, good afternoon. Let's see. What I was gonna do today is start with some administrative stuff. And then so if you guys had any questions, and then talk a little bit about the reading materials that you guys had. You know, whether you guys did or not. By the way, guys, can everybody make sure they're muted? There's some like background noise stuff running around. Anyway,
That's me.
No worries. So talk about the stuff in the lectures, and then I'm going to talk about our project one, which I snuck up on the canvas for you guys to appreciate. Okay, so administratively, so, you know, like I mentioned, I'm doing something new with you guys this semester. There's no midterms, final, etc. We just have projects and presentations. So the downside of that is I'm kind of I'm figuring this out as I go along. So, you know, the presentation that you guys have is something that's going to be running probably like, you know, 12 weeks, 14 weeks, whatever. We just need to finish it by the end of the class. And in between, I'm going to be like sort of sorting out, putting in, weaving the projects. And we might have, I don't know, maybe 4, 5, 6, I don't know how many projects we're going to have. We'll see how many we can get to. And so it's not like a consecutive where we're like, every week we're working on the presentation. You guys, you know, there's a few of you, the teams that we're gonna try to see if they found another chip besides the one they had, because there was some dabbling up or maybe stuff that you guys decided you didn't want to work on. And some of those guys actually got back to me with some options. I think there's still maybe a couple outstanding, but anyway, so long story short, unless you have a specific question about the presentation, I wasn't really going to get into the presentation this class, but the only thing I was going to tell you guys is in regards to the presentation well, before I say that, the other downside of what I'm doing is I really am not going to have any idea like how much work it is for you guys to be dealing with presentation and projects. So, you know, if it's too little or too much, probably I won't hear about it if it's too little, but if it's too much, let me know. But basically the idea is that this project one, which I'm giving you guys, I was going to ask you guys to turn in the project results by like next Friday. So bring it to the class so we can talk about it. So next Friday, what is that? The 18th. So that's the due. And hopefully it's pretty simple. And then the presentation wise, also next Friday, what I'd like to see from you guys is a cost estimate. So this is a estimate for chip you're replacing. Okay, and that's going to come, I'll put this in the announcements, but it's going to come in sort of 2 flavors, right? One of them is the NRE for the new project. Well, now let's not get too ambitious. Let's just do the cost. Okay, so what I'd like to do is what you have to do for this is you have to try to figure out the die size. Die just means the size of silicon chip size for your replacement. for the part you're replacing, for, let me put this better, for the part to be replaced. And from there, you also have to figure out or guess, or no, if you're gonna figure it out or you're gonna guess, either the die size or the process technology, what I would like to see from you is why did you think that? I guess is fine, but you need to like back it up with some assumption. So you got to figure out what process it was made in. And between the two of these, you can get the try to get the silicon cost. Again, this you have to make some estimates on yield. And then plus other costs. These would be like test costs, packaging costs. But ultimately, this is what you're replacing. This is going to be your competition. So a lot of times at work, in business, etc., you are Brianna asks, is the process is the nanometer size? That's correct. Yeah, for instance, like Brianna is saying, a 7 nanometer process or 45 nanometer process, etc. Exactly right. So most of the time, or a lot of the time in the real world, this is the real world, in sort of industry, say, you're guessing at stuff. And what people want to see is that if you are guessing, so they want to hear, are you guessing or you know for sure? And then if you're guessing, why you're guessing that. And then you can have some discussion about it. And either you can say, well, that's not a good guess, or you say, guess isn't good enough in this case. We really need to find out, or okay, we'll proceed with that guess. That's how it goes. So for example, you picked a chip that was made by a big semiconductor company in 2005, say. We could guess that that's probably having, without any other data, let's say we can't find data, we might guess that was at a 45 nanometer process. Why? Because that was kind of the mainline leading edge production process back in that day, and this chip was made like, you know, for that kind of purpose. Let's say you got an Arduino chip from, this again, I'm just telling you guys like the guessing procedure in case you cannot find the actual answer. Let's say you got an Arduino chip from like 2016 and you go, well, you know, these guys, it's an Arduino chip, you know, I don't know if the volume's going to be so much. It's made by a small ASIC company. Those guys probably wouldn't be using a leading edge foundry process because it would be too expensive. You know, I'm looking at the clock rate for this chip, it's not that much. So if I was them, I would have also, even though it's 2016, I wouldn't have gone into a 28 nanometer process. I would have stayed with the 40 nanometer process because it would have been, I can get everything I want there. The cost makes sense. So this is sort of like what I mean by like sort of guesses. The other places you can guess is we can look at the power supply of the chips. It's kind of hard somewhat, but you can kind of look at if some stuff's like at 1 volt power supply, it's you know, like a 1 volt. We haven't gotten into this yet, so I'll mention it. So if you look at the power supply for your chip, most chips have something called core power supply, and then they have like IO power supply or other power supplies. So what I mean is the core power supply. This means the logic inside the chip. Yeah. So sorry. Let me. Paul's got a question, but let me finish my thought here, and I'll talk to you guys about it. So 1 volt supply. You know, this would probably mean The problem with the 1 volt is things have kind of stayed at 1 volt for a long time. This could mean anywhere from probably means like you're at less than 40 nanometers. Okay, if you're at 1.2 volts, it might mean you're at 1. So you're at 130 nanometer to 90 nanometers, say. And if you're like at less than 1 volt, means you're probably at, you know, like smaller than 22 nanometer kind of thing. So this is, again, not an exact science. You're kind of like trying to look at all this stuff and trying to estimate, you know, what you guys are doing. Okay, like finding these costs. So again, this project, the presentation is a work in progress. So what I'd like you guys to, Paul is asking if you should make a PowerPoint, and the answer is yes. And like, just keep adding to the PowerPoint that you got. So this is one of the things I really liked that we did at work, is just new every week as you're getting more information, it just sort of shows up at the top of your deck. So like, let's say, you know, you have 3 more pages or 3 updates, slides this week, you just make the previous presentation start on slide 4 and you just plug this in. So you kind of have a record of what happened historically. So yeah, so this is for the information, this is for the chip you've decided to replace. Okay, so you're gonna give it your best guess as, so we're gonna figure out, so in that PowerPoint, you'd want it like an Excel table, cut and paste it in the PowerPoint. And you want to say that says, okay, what's my die size, right? And then you're gonna, in the PowerPoint or in the table, you're gonna say like why you thought this was a die size. Maybe it's, you saw it in some paper, or they announced it like that, or you're just sort of estimating it. But I want to know why you're estimating a certain die size. And then you're gonna put in, you know, certain process, and then why you think that's the process. Okay, then you're gonna go, well, okay, so I'm gonna assume the wafer price for this process is X, and I like to hear why you think the wafer price for a particular process is X. And then you're gonna plug in the die size into that. You know, I think I showed you guys a website with the gross die per wafer calculation, where it gives you how many dies you get and what the yield might be. And then you're also so assuming some yield, and I want to talk to you guys about why you think some yield is appropriate. Again, this is a work in progress. So the whole point is, we, as I see this stuff, we can talk about it, and we can, it's to help you guys think ahead and engage with me, but to come up with these numbers so that it'll stick. And 2, it's a little bit of, what's the word? I forgot what they talk about. It's a play acting. No, it's not the right word. Sort of rehearsal, let's say for you know, the work environment, where that's how it goes. You know, you sort of present something to the rest of the team or management, you give your reasons, there'll be some discussions, say, I think you're right, you're wrong, whatever, you're off, the, you know, whatever. And then you rev on that. So you keep going. Okay. Anybody? So keep it loose for this next Friday. Just go with what I'm verbally telling you, and then we can tune your presentations as time goes, as you guys see what I'm looking for. Any other questions? So just remember, make your assumptions. What I'm looking to see from you guys is whether you've got, you know, whether you've thought through all the different costs potentially, whether, you know, what your thoughts are about what the, you know, not only what line items there might be for the cost, but what the costs may be, Have you missed anything? What your thoughts are on why such and such a thing could be true. And again, like a lot of it, you're just gonna have to guess. Okay, so it's not like I'm looking for you guys to be right or wrong. I'm looking to engage you guys with you guys in discussions about how you're thinking about this cost per chip. Any other questions, guys? No?
All good, Professor.
All good? Okay, sounds good. So I will leave it at that. So that's the next step in the presentation for next Friday. And then any questions about that? I mean, I guess you guys said no. Any other questions so far about anything?
We're getting,
Go ahead.
Professor.
Yeah.
Are we in person by next week?
We're going to be in person next week. Yeah.
Got you. Thank you.
And what I was planning to do, the E&M class told me that prefer for me to just like sit in the corner of the class and sort of just write on my iPad like I'm doing here. So you'll have a recording and maybe it's easier to see. So I'm projected, obviously. And so assuming all that stuff works, that was my plan. But if you guys want me to be on the whiteboard, I'm happy to do that too. So we'll play it by ear.
Would you recommend us getting a laptop for class?
To bring a laptop to class? No, I'm hoping I can project it. If I can't project it, I'm just going to do it on a whiteboard.
Okay.
Yeah. Oh, sorry, guys, at my brother's house. Okay, cool, guys. So today, haha, I'm going to start talking about stuff, some background stuff. For the presentation, you want us to just bring a USB. You could just bring, yeah, that'd be fine if you guys bring a USB. Or, shoot, I did not do what I said I would do, which is get a Microsoft, whatever the heck that was called, online storage, so you guys could dump the stuff. OneDrive. Thank you, George. So I'll do that, but if that doesn't happen, you guys could also just email it to me and I can project it up and you guys can tell me to like go forward and back and all that stuff. So I wouldn't worry about USB keys. You just email it to me, or we figure out the OneDrive business and put it up there. Or you can bring the USB key, whatever you guys like. All right. Okay, guys. So I'll start my thoughts here. So unfortunately for you guys, a couple of the two things I enjoy in life is like physics and history. So I always got to weave history into what we're doing. And but I'll give you one ahead of time. I like doing that. But the reason is there is a good reason I do that, because I'm thinking back to my undergrad days. I'm constantly looking back to my undergrad days and trying to remember what I was constantly confused in my undergrad education. And I try to think back about why I was confused. And a big part of why I was confused is I had no context about anything we were doing. And because I hadn't started working yet, it just seemed like different subjects would come and go and like I wouldn't have an idea. So anyway, I'm just trying to do my best to give you guys some context. So here's the context for what we're doing in the class before we sort of peel the layers of the onion. So, it's like I was listening to this podcast the other day, and they were musing about whether sort of scientific and technology progress is kind of, like continuous. Like, say if this was time, then this was something called progress. Whether it was just kind of like doing this with time, which means like, hey, like every generation, we all are contributing a little bit, nudging along this thing, or whether it's like kind of like this, where you're going along, then so basically most of us are morons, not contributing. Then you get Newton, and then like nothing happens with the rest of us fools, and then Einstein pops up, and then so on and so forth. So is it like these brilliant individuals create these amazing things? And that's like, if you took these guys out of history, we would still be like, we wouldn't be figuring out how gravity works if you took Newton out of history or something. So the reason I mentioned that is because there was a gentleman who, so my view of the history is more like this, I guess, at the moment, about technological progress, which is like these discrete steps with these, giants in their own individual fields come in and really like changing things or creating a significant step forward. And one of these huge steps forward, again, these are all different fields, so it's not like it's a continuum, was this guy named Claude Shannon, who only passed away, I guess, in 2001. So he was doing his work sort of in the 1920s, or the more stuff he's famous for, to the 1940s, maybe late 1940s. So pretty recent. And I don't know if I would put him in like the same league as Einstein, say, I don't know, but probably was. But he's known as the father of information theory. Okay, which is like sort of everything that we're doing. In fact, I was looking him up earlier today, and it said he had invented binary computation as part of his master's project, which was kind of cool. Okay, so why am I mentioning him? Because because along his father of information theory, one of his many contributions was the concept of binary computation. That all our computers are based on. Okay, so if there's like a simple, I don't think this was in his paper or papers or dissertation, but here's the way to look at it. Okay, this idea. So let's say, basically the idea of binary computation / communication is that binary communication or computation protocol is more efficient than other numbering systems. Okay, I'm not an information science guy, so this is just the world according to Barmack. The computer science or information theory people in the class, they're probably having a heart attack as I'm talking, but this is just the way I see the world. Okay, so this is binary communication or binary computation is most efficient. So here's an example that I read about in this book that I thought was kind of cool. Okay, so here's an example of different communication protocols. Let's say you have two ships, right? You have ship A, ship A and ship B. And, I don't know if you guys have watched these old movies, but, when the radio breaks down or before they had radios or whatever, what they would do is they would put up some flags with, they're communicating with flags. I would put up a flag that says something, and the other guy would, put up a flag that says acknowledged, and then it would say something, and I would go back and forth with these flag signaling. Okay, so let's say you were going to communicate, the only thing you were going to communicate was a number between 0 and 126. I'll tell you guys later why that's the case. Okay, so that's what you were communicating back and forth. Each one of these numbers indicates something. whatever it is, go forward, turn left, turn right, stop. Okay. So the most, and you wanted to keep the number of flags you got to store to a minimum. Okay, that's our efficiency. So communicating this range of numbers and the number of flags we have to have on this ship shows how efficient we can be. Okay, so kind of the least efficient, most straightforward thing you could do is you could have how am I doing? Sorry, 0 to 127. The least efficient thing you could do is you could have 127 flags on your chip, each with a number on it, right? And you want the number 20, you put up a flag with the number 20 on it. The guys go, okay, that means blah, we'll do whatever. Okay, that's the least efficient. You need 127 flags. Okay, now if you get a little smarter, you might decide to do some kind of a decimal thing in the sense that you would have a set of, you'd have like, say, three types of flags. Okay, you would have a flag for this, the whatever 0 through 9. You have a flag for 10 through what is it, 10 through, no, wait a minute, you'd have a flag from 0, no, it'd be from 10 through 99, I guess, and a flag for whether you're below 100 or above 100. So let's say what I mean. So you'd need flags going 0, 1, 2 to 9 in the first digits. So that's 10 flags for the least significant bits. Okay. Then you need a 0 flag to denote, if I'm at 1, I need to put 0. So let's say if I'm representing 1, my flags would be 0, 0, 1. If I'm doing 0, 0, 2. But then if I want to do 11, I need a 1 flag here, right? And I keep that at 0. And so I need the same number here. So if I want to transmit the number 99, I want to, this flag to be 9, this type of flag to be 9, this type of flag to be 9. Okay. And then if I want to do 127, I need another flag here, and I would pick 1, 2, and 7. So basically I need 10 flags for the least significant bit. I need 10 flags for the next one. And then I need 2 flags for that. So I can do 22 flags if I just have different flags for the different digits. Did what I just say make sense? I don't know if I explained it well enough. What are you with me? Okay, so just by doing this, so instead of looking at 127 flags, just by looking at this as the significance of the digits, still staying with the decimal numbering system, I got whatever, a factor of 6 in efficiency in the number of flags I'm looking for. Okay, so now let's say you go to a binary system, math systems. Okay, so what you need is, let's say for a binary system, the reason I picked 127 because that corresponds to 7 bits. Okay, so that corresponds to 0. And I get tired of assuming you guys can do binary math, but what the heck. So that is 1, and that goes all the way to 1, 1, 1, 1, 1, 1, 1, and this is 127. Everybody with me? Anybody confused? Don't be shy. Everybody with me? Okay. So basically, in this counting system, in the binary method, you need a total of 14 flags only because basically for each bit, you just need 2 flags, either a 0 or a 1 for each of these positions. Okay, so I went from 127 flags to, I don't know if you want to call this a decimal system, to 22 flags to 14 flags. Okay, this was meant as like a really brain dead demonstration of how binary communication is much more efficient than sort of decimal communication. This is what part of what Shannon sort of is probably mislabeling what he said, but this is sort of a cool demonstration of what that means. Basically doing binary math, both in communication and doing the math, is very efficient. And that's why you like to do binary communication if you can. Okay, so there's like, I'm sure you had a much nicer proof than this. Any question about that? No, you guys are very quiet. Okay, so this is like, let's say he came up with this in whatever 1920s, and like it's really interesting from a theoretical standpoint. But you know, the problem with binary communication or calculation is you need potentially a lot of switches, a lot of circuitry. Okay, so here, if I want to, let's say, add to, let's say in binary communication or computation, let's say I want to do some math, I want to add a 7-bit number, so A, which is a 7-bit number, to B, which is a 7-bit number. Okay, so this needs a 7-bit adder. And, you know, I'm not sure how many transistors that takes. That's like a bunch of flip-flops and NAND gates and all that stuff. But for the sake of discussion, so just don't quote me on this, but for the sake of discussion, let's say if you did this right now digitally, you might need something like 500 transistors. Let's say that. Okay, and I'll come back to what this means. Okay, if you did it digitally in a binary computation way. Okay, but you can do this if you can think of this decimal or sort of this brain dead communication. You can really think of this as being an analog summation. So let's say I want to do the same thing. I have A, which represents, let's say A, the range of A goes from 0 to 12.7 volts, and B goes from 0 to 12.7 volts. And so this A has got a bunch of discrete steps. Each one of them is 100 millivolts. Okay, so A can represent 128 levels. And B also does the same thing. B does 128 levels. I can make an analog adder. So this is analog computation. I can make an analog adder, which is just, you know, a couple of resistors. So this is A, B. These are in volts. Volts. Okay, I don't know. Make that. So this is VREF. So I make an amp. And this is A plus B. I mean, with some ratios and stuff. I didn't bother doing the exact calculations, but basically something like this. Okay. And let's say I can design this op amp in 16 transistors. Okay, so believe it or not, so just because you're doing computer math doesn't mean didn't always mean you were doing binary math. Initially, believe it or not, a lot of computer math was analog computation. Okay, when transistors or vacuum tubes or those kind of things were precious, means you had very few of these active devices. It was like it was like, so what that this dude, this Ackett, no, it's not like it was worked for AT&T, for Bell Labs. But so what that this guy, the scientist type, came up with this efficiency business. That's fine. I don't have 500 transistors if you were like sitting there in like 1960 or 1970, thinking about it. I have, 16 transistors. This is just like a theoretical thing, whatever. I'm doing, I got to do the calculation in an analog way. And in fact, this was what was happening. It was like at some point in the 80s, now let me take a step back. So this was what was happening. But there's lots of problems with analog computation. If you do it this way, first of all, it is inefficient. Then as you can imagine, if you were trying to add two 12-bit numbers, the number of steps here, each one of these, instead of being 128 steps, at 12 bits, you would have to have 4,000 steps here, which means and that means the size of the steps are really tiny in the voltage domain. Each step might be, I don't know, like a millivolt now instead of 100 millivolts. So if you just have a couple of millivolts of noise, you've got the wrong answer, right? I mean, it's something to have at 100 millivolts. That's a lot of signal to noise ratio on each one of these steps. But if these shrink to a millivolt or less, then you've got a serious problem, because those are the kind of the noises you would expect in your analog system. So the other thing binary communication does is it gives you a lot of noise rejection, as we see, okay, which is one of the key things. But so long story short, there was an incentive, sort of a theoretical incentive, to do binary computation, to do digital computation. But assuming you had a bunch of transistors, and assuming that those bunch of transistors didn't cost you a ton of money. So basically it was an economic question. As long as 16 transistors was what was economically viable and 500 transistors was just too expensive, you wouldn't do this. So that was the incentive, okay, coming back to chip design. So this is where we're talking about sort of binary computation and information theory. So if you guys remember, the first lecture, I was talking about Moore's law, okay, which you want to keep increasing the number of transistors per chip. Every 18 months, they were dabbling this. And another way to look at this is the cost per transistor was going down every 18 months. It was, another kind of roughly, it was getting cut in half every 18 months. And this being an exponential thing, it was like a very fast transition. So pretty quickly it got to the point where both this 500 transistor number and this 16 transistor number were both basically the same number. The cost for either one of those was pretty close to zero. Okay, if you're looking at, like I said, you can put in right now, you're looking at 20 billion transistors in a typical chip, and let's say a typical chip is $50 or $100. Whether you've got 500 transistors there or 16 transistors, who cares, right? Doesn't matter. So anyway, what happened as you get these generations of CMOS technologies, the transistor costs came down, the number of transistors per chip went up, is more and more of the world became binary and digital, and less of the computation ended up being analog. And I think that, believe it or not, probably the break even was probably, I'm gonna guess, in the early maybe sometime in the 80s or 90s, where you went completely, like all signal processing essentially became digital, and all computation eventually became digital. There were like all these little islands. For whatever reason, you needed to do something in the analog domain, and eventually they all went away. Okay. So there was a huge incentive, economic incentive from a performance standpoint, et cetera, to put more transistors in a chip. Okay. So by the way, just as an aside, this analog computation is making a comeback, like nothing ever completely goes away, in neural processing chips, because for various reasons, I don't, I'm still up in the air, questionable whether the thinking is really correct or not. But anyway, believe it or not, it's coming back, and some of this neural processing chips are considered doing analog computation. In fact, I'm attending a conference in a couple of weeks where there's a discussion, there's a forum about that, which one's more efficient. So nothing ever completely goes away. Okay, so this was my really long-winded description of yeah, faster. Yeah, George is saying it might be faster to do analog computation. Yes. Sometimes it's lower power consumption. Like a lot of things come into that. A lot of thoughts go into it, depending on what you're doing with the system. But so anyway, that was my long-winded description of why we are where we are, in the sense of why are we doing these chips? Why are we building these digital chips? Why is it digital? Why is it binary? And so does that, any questions about that whole concept of why we're binary, why we're digital? Again, half of you guys are computer science, so you probably know better than me, but I just thought I'd mention that because it's always like, well, why the heck are we doing what we're doing? Okay, so big incentive to get more transistors on a chip. Okay, so that was so it's kind of heartwarming from being an engineering standpoint, that somebody could come up with a theory showing that theoretically something is more efficient, and then economically that picking up speed, and I'm talking about, God knows how much has gone into microelectronics. Trillions of dollars over the years have gone towards making this happen, right? They're like the whole economic system of electronics, microelectronics, computers, networking, blah, 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 is based on this theoretical musing back when you couldn't even really build this thing for various reasons. But just sort of like, it seems like once engineers or the technology business or whatever got the, sort of latched onto it, it was just made it happen. And so here we are with Google and Apple and Facebook, and basically the whole digital world we live in is based on Dr. Shannon's thoughts. It's very cool. Okay, so now, so let's say we just love lots of transistors in a chip. To do binary computation plus communication. Okay, So, okay, so that's what people started doing. And there's different, the reason, okay, so this is the reason we're doing binary. The reason we're doing most of these chips or all these chips, or why this class is almost entirely in, it is entirely in CMOS technology, is it turns out that CMOS was the technology that could get the most transistors in a chip. Okay, so that's why it won. It wasn't because it was the fastest. It was not the fastest technology. You name it. It wasn't for anything else but for power consumption. Okay, simple and clear. That's why CMOS. So this is a really long-winded way of me coming back to why CMOS is constructed the way it is as a logic family. Okay, so it's all because of power consumption that was just kicked everybody's butt in terms of power consumption compared to other logic families. You guys probably haven't even heard of the other logic families that existed, like TTL and I don't even like CML. And these are all logic families that like were around in the 80s, 90s, some part of the 90s, etc. But they didn't survive because CMOS was the lowest power consumption. What else do I want to say about this? Okay, so let's sort of coming back here, say, what is it about CMOS that makes the CMOS logic family? So this is CMOS. So there's CMOS stands for, as I mentioned, stands for complementary metal oxide silicon. Okay, so for those of you guys who are not electrical engineers, this metal oxide silicon is a type of transistor. And complementary means you have both N and P type transistors, PMOS, NMOS. We're going to be talking a lot about this stuff. So if this doesn't ring a bell, don't worry. So in one sense, that's what it means. In another sense, it means something pretty specific. It means so that says sort of in sense one. In another sense, it's referring to, whoops, was this Arab? As you can tell, I was teaching electromagnetics a couple hours ago. So sense two, it's a very specific circuit topology. And what's cool about this circuit topology? It's very low power consumption. Okay, so I'm going to show you guys what this circuit topology looks like and why it's low power consumption. And then we're going to go down and like lecture after lecture, we're going to like really dig into these things. So guys, let me catch up to the questions. I don't know, because in order to addition, you need to identify voltage steps. You can only have so many. That's right. Yeah. So precision, number of steps, signal to noise ratio. So lots of trade-offs, but digital is one for mostly for signal to noise ratio. And as you guys will see that. And it's a very long discussion. So I'm like brushing by a lot of things, but that's the upshot. Okay, so let's talk about CMOS technology. I keep thinking I want to tell you guys something else. And I keep, okay. So, okay. So I'm going to talk about what this topology or this logic looks like. Okay, so but let me take a sidebar here. Okay, so when you're doing binary math, so I kind of drew a circuit here, an amplifier. Okay, and I could dig in a little bit more in here if I made it with, you know, CMOS amplifier. I would have a diff pair coming in. I would have like, you know, load. I would, you know, I could build this guy up. Whatever. I don't know, just some random amplifier I'm drawing here. Okay. So that's what this would look like. Okay. When you're doing binary math, you're not working with amplifiers, right? You want to basically do Boolean functions, binary Boolean functions. Okay, so what do you have? You have inversion. Okay, that's a base function, and that you do with an inverter. So you put in, out. So your ins might be out. In would be 0, out would be a 1, in would be a 1, output would be a 0. Okay, so that's pretty core. Then you would maybe have a NAND operation, NAND 2, which means, by the way, NAND 2 shorthand for 2 input NAND gate. Okay, so that symbol for that is like this. This is just like binary operators out. So that one looks like A, B out. And then would be 0, 0, 0, 1, 1, 0. By the way, usually, no, I mean, I'm not going to confuse you guys. But anyway, NAND, sort of same as AND. Why am I'm going to confuse the heck out of you guys. See, I cannot say any sentence without a bunch of qualifications, because each one of these, there's a reason why. For example, why am I saying NAND and not saying AND? Right? Why am I inverting the output? It turns out that it's easier to make NANDs in CMOS logic than it is to make ANDs. Okay, AND gate is more transistors than a NAND gate, and you can do the same logical operations if you had NANDs and inverters and NORs than if you had ANDs and ORs. But you couldn't do it the other way. If you just had AND ORs and buffers, you couldn't do everything you could do with inverters, NANDs, and NORs, if that makes sense. But anyway, so anyway, so CMOS likes CMOS logic likes inverting gates. That means you won't see any CMOS AND gates, or they tend to be a CMOS NAND gate with an inverter. So CMOS AND gate, AND 2 looks like a CMOS NAND gate plus an inverter to make the output non-inverting. So this has more transistors than a NAND. Okay, so that's why a NAND. Okay, so back to our NAND. The way the NAND works is it is high, except when both inputs are high. And then a NOR 2 is also very popular, NOR 2. And that looks like this. A, B. So it would be 1, 0. Okay, so these are kind of, these are typical things that you use. You know, you might have a 3-input NAND or AND, or a 4-input NOR gate, that kind of thing. But these are the components you need to do binary math. Okay, everybody with me? So anyway, binary better than decimal or analog, whichever way you want to look at it. And then to do binary, we need gates to do Boolean functions, because that's how binary math is done. Everybody with me?
Yes.
Okay, so that's what this sends to. So we're gonna make a bunch. We want to basically make these kind of Boolean functions from these transistor types. That's what the second sense is. It's a very, very specific circuit topology to make these kind of gates out of NMOS and PMOS transistors. By the way, anybody not familiar with MOS transistors or PMOS and NMOS? How are you guys doing out there? Anybody? Who do I pick on? Who do I pick on? Julio.
That's why I literally just replied. But yeah, I was gonna say I'm a double E, so I feel like I'm pretty familiar with them at this point. And most
Okay.
of the classes I'm taking use them.
Okay, perfect. Let's see. Brianna, how are you doing with PMOS and MOS?
I've worked with them a little bit in 2200.
Okay, cool. Cool. Okay, sounds good. I mean, we're gonna go through it in gory details in future lectures that you guys will watch. But for now, let's just say PMOS and NMOS, and we're gonna make pretty specific gates. Okay. So now,
So most of the the chips that we've used for our previous classes are all based off CMOSs, right?
I would guess like 100% of the chips would have been CMOS digital chips, right? It's possible you would be using a chip that's like a voltage regulator. That might be bipolar. Or if you were doing an RF class, or I don't know if you do this in Cal Poly or not, but let's say you were doing a radio frequency circuit and you had the output of your chip drove a power amplifier to drive the antenna out. That power amplifier may have been bipolar, or the low noise amplifier going from the antenna to the chip may have been bipolar. But the digital chips that you use are all going to be 100%. I mean, I don't even want to say 99.9, 100% CMOS. So all the chips that you guys presented, stuff AMD, Intel, stuff from Qualcomm in your cell phone, Arduinos, FPGAs from Xilinx or Altera. It's almost, everything is CMOS at this point.
Thank you, Professor.
And again, it becomes like, because the other logic families that existed that were not CMOS, if you try to put 20 billion of those transistors in a chip, that would just explode. The power consumption you wouldn't be able to deal with the power consumption. So that's why, essentially. Okay. All right, so we want to build these gates. Okay, so now, and we got PMOS, P transistors and N transistors. And as you guys know, so each one of these has a gate, source, drain. And there's the body substrate connection. There's a substrate connection. So these things are pretty complicated beasts if I want to look at them as, analog entities. Okay, so we got, don't get worried here. I'm just telling you guys like how deep you could go into this. Well, it's like whether you want to think of it as like a 3-terminal or 4-terminal device, there is like a relationship. Let's say if I take the NMOS and, I should put the relationship between the drain source voltage and the current going through it, through the drain. I have these, curves at different, very complicated curves at different VGSs. We'll be looking at all this good stuff in detail. And then if I look at the gate source voltage versus the current, I might have all sorts of goodies here with different VGSs. It's all like complicated, and we'll look at the second, third order effects as time goes on. But for the sense of this lecture, so this is like also degrees of simplification. You can start by, if you just want to look at the core topology of CMOS logic, you can just try to imagine for a minute that these guys are just simple switches. Okay, so think of it, for the sake of our discussion today, we're going to think of them as simple switches. Okay, and at the beginning, we won't even be thinking in terms of voltages and currents or anything. Let's just think of it in terms of zeros and ones. Okay, so I'm going to model the NMOS. I'm going to pretend the NMOS is like a switch. Okay, that works like this. If the gate is high, okay, the switch is closed. And if the gate is low, the switch is open. And the PMOS, I'm going to pretend it's a similar kind of switch, but the relationship between the gate turning it on or off or open and closed is going to be inverted. So for a gate of 1, whatever that 1 is. Now that 1 is like a theoretical thing. It's going to correspond to some voltage, as you'll see. But for a gate of 1, it's open. And for a gate of 0, it is a closed switch. Okay. Any questions about that? Okay, so let's say I want to first, let me draw you guys a couple of gates, CMOS gates, and then we'll generalize from there. So first, let me show you guys a CMOS inverter. Okay, so again, the table for it, this is the symbol for an inverter. The idea is when the input 0, I want the output to be 1, and when the input is 1, I want the output to be 0. So how do I build that? Okay, so what I'll do is I'll put a PMOS and an NMOS together. I hook up the source of the NMOS to ground. I'm going to hook up the source of the PMOS to the highest voltage I have in this chip, or that's available for the core, and that's called VDD. Okay, just so VDD is supply voltage. And ground is ground. Okay, then I'm going to connect the inputs together, the gates together, and I'm going to call that A, or the input. And the outputs are connected together already. And I'm going to take my output from there. Okay, and then if I look at the substrate connections, I'm going to also hook these up like that. Okay, so that's a CMOS inverter. Okay, so let's for a second say that VDD. So the highest, the supply voltage corresponds to a logic 1, and ground corresponds to a logic 0. Okay, so when I put VDD here, so that would be a logic high. I want ground to come out of here. Okay, so if I have a logic high input, I want the output to be a logic 0, because remember, this is an inverter. Okay, so according to my little assumption here on these switches, let's see what happens. If A is 0, so A is 0, okay, what happens is A is the gate, right? A is the gate for both the PMOS and the NMOS. So if A is 0, the PMOS is a closed switch and the NMOS is an open switch. So this becomes, whoops, this PMOS becomes a closed switch. And the NMOS is an open switch. Okay, so this is with A equal to 0. So logic 0. Okay, so my out here is connected, is disconnected from zeros. So it can't be 0, right? It's disconnected from ground because my NMOS is off. And it's connected to a 1. So out, it just becomes 1. Or voltage, in the voltage domain, it becomes VDD. Okay, so A is equal to 0, input's equal to 0, out is equal to 1. Okay, and then if I have A is equal to 1, my switches are gonna look like this. So VDD, or logic 1, I'm gonna have the PMOS is gonna be open. Again, A goes to the gate of both P and N. Okay, so this is key to CMOS logic families. The input goes to, so, okay, actually, let me do this and I'll come back to the general statement, sorry. So the PMOS is open, the NMOS ends up being closed. And so now out is shorted to ground or to logic 1. So out becomes 0 or ground. Okay, and again, so this is what I'm achieving. So basically this circuit with the P transistor on top, N transistor on bottom, the P transistor connected to this high supply voltage, the N transistor, the other end of it connected to ground, both inputs connected together and both outputs connected together, or both drains connected together and being the output, makes a inverting function with this assumption that they act, these transistors act like this simple switches. Any questions about that, guys? About a CMOS inverter? Okay. All right. So for your lab, what I'm asking for you guys to do is to draw this in SPICE, put in the appropriate supply, ground, input, output voltages, and show with the waveforms on the input and output that you indeed have an inverter. Okay. So when that's your, and then, you know, there's on Canvas, there's a sample LT SPICE deck that you guys should
Professor,
play around. Yeah.
I
go ahead.
actually looked for it. I didn't find that sample. Did you just upload it or?
Let me see. I thought I put it in like a week ago or something. It's called LT-Spice template.asc. There's a module called LT-Spice.
I'll look for it.
Anybody else gone looking for it? No?
Someone
Look for
said
it
they
right now.
found it.
Okay, well, let me do a little, let me actually play with that right now. So, because that's the other thing I wanted to do is to show you guys, give you guys a little tutorial. There's also a tutorial video, but just as I'm showing you guys the inverter, man, I really love not having to follow my slides. Is this what I'm saying? Is it confusing, by the way, or are you guys kind of just generally able to follow?
No, we can follow.
Okay, because I feel a lot better about meandering this way because it makes more sense to me than having to follow my slides. But so, and it gives me a chance to be a little bit more, anyway, sensible. Okay, so I just talked about the CMOS inverter. I'm gonna come back to that stuff, but it's a good segue and maybe a little bit break to talk about project one, which is to, so there's three problems: an inverter, a 2-input NAND gate, and a 2-input NOR gate. And what I want you guys to do is to draw these out in LT-Spice or the Spice of your liking. But again, LT-Spice, I have it. I can help you guys debug it. The model file is already in that, hopefully is in that example. So you guys don't have to worry about finding the model file or importing it and so on. So here's how I'd like the presentation to look like. Okay, so again, the first page, just your name, project, email address. Please also put in your name in the file name of the PowerPoint. Okay, so, by the way, so in sort of industrial domain, I don't know how much you guys use Word versus PowerPoint for your projects, etc. But people use PowerPoint much more than Word. You see a lot of reports being in PowerPoint, essentially reports. It's not, a lot of reports don't end up being kind of a Microsoft Word document. They're in a PowerPoint format. Okay, because you essentially end up presenting them, but a lot of times people just look at them when you're not there, but in the form of a presentation. They hope that it's sort of it's distilling the information, sometimes true, sometimes not. Okay, so the second page, I always like that to be an introduction, and that basically tells the reader what you're doing and why. Okay, because it's not always clear. Like in this class, when you're handing me project one, I know what you're doing and why, but that's because I kind of told you. But a lot of times people are again, at work, people are like looking at your slides and they're going like, why, what are you doing? You're, some management guy 2 levels up from you is reading that set of slides a month after you put them together. He didn't attend your presentation. He doesn't realize that your manager told you to do this, or this is the biggest problem your group is facing. He's just looking at this thing and going like, why did you do this, right? So that's slide 2. Third page, this is a really, really, really important concept for all you guys, is the concept of executive summary. This is important in slides, it's important in written documents, it's important in long emails. Is the reason it's called executive summary is because this problem mostly afflicts management, but it's like pretty pervasive in everybody. But basically, most people are just gonna read this. Most people are gonna look at your 20-page slide deck. Most people, I mean, the people in your group, other people working on the project, maybe your direct customer is gonna look, parse through every page of your slide deck and pick it apart. But again, the director of the department, he doesn't have time, interest, attention to read your whole slide deck, or at best, he's gonna like flip through it. Okay, so it's always good to put, or I think essential, not just good, to put an executive summary clearly labeled that says, hey, if the reader was only gonna see that slide or that paragraph, if you're doing a written report, or just read these 3 lines in your long email, they would get the gist of what you did and what your results meant. Okay, like that executive summary would say, like, a environmental test was done on the battery on this laptop. Engineering department strongly recommends recall of these batteries before they kill somebody. Okay, that's like in your executive summary. And all the other slides after that, we'll talk about how you did the tests on the batteries, where this issue come from, root cause analysis, under what conditions do the batteries blow up, in gory details, right? But the CEO of the company, you want to make sure he gets the message that, this is the of course, most presentations aren't that dramatic or that key, but maybe you're just saying, we recommend the project schedule to get pushed out by a month. Or the summary might just say, at this point, we don't see any risk elements, full speed ahead, no reason to do it, or whatever you want to say. Whatever your message is for this project, you always have a message. Nothing you are reporting to anybody else is ever neutral. But a lot of engineers, unfortunately, give neutral presentations of numbers, and they're expecting the audience to draw a conclusion from it. You should tell the audience what conclusion they should pull from it. Believe me, in an engineering environment, if they disagree, they will disagree with you. Or if they disagree about how you did your tests or why they come to the conclusion, they disagree with you. But you should always be telling them how you see that story. Okay. Anyway, long story short, that's the executive summary page. And then you're going to go through a bunch of slides, or however many pages you need, to tell the audience what you did, whatever details you want. And then at the end, you need a conclusion, okay, summary slide that says, this is what I did. So first you tell them what you do in the introduction, what you're going to do and why. Then you're going to do it. And then finally, you're going to tell them in one slide what you did again, because a lot of times, these are the only slides that anybody will see. Okay. So the other thing that it's like a real pet peeve and a must, is all the graphs, etc., must have clear titles, axis labels, and units, and those kind of things. Okay, so that's your requirements for the format of the presentation. And this is what I'm looking for for the project slides. Okay, so this is project 1. Okay, so now let me pull up LT Spice. Where are we? So you know what, guys? Let's take a little break. And then when we come back from the break, I'll start on this LT Spice business. So let's take a break till 2, so like a 11-minute break until 2:30. Okay.
Yeah.
Yeah, you can.
Yeah.
We can hear you.
Awesome. Okay, great. Thanks, guys. Are you guys able to see my the little spice schematic thing here?
Yes.
Okay, good. So this is on my Mac. I have LT Spice up. Again, you know, I know some of you guys use PSpice and so on, so feel free to use it if you like. But again, this is what I have. It's not like that I'll refuse to help you guys if you're trying to debug PSpice, but it'll just be harder for me to do it. So if you have LT Spice, it's easier. Okay, anyway, so this file should be on the canvas. I hope it's there. So what does it show? Okay, so first thing is it's showing this schematic, and from our discussions here, you guys will notice that this is a CMOS inverter here. I have an NMOS transistor going to ground. I have a PMOS transistor connecting to the supply voltage. In this process that I randomly picked from the internet, the maximum supply voltage is 1.1 volts. So supposed to be a generic 45 nanometer process, okay? And notice how the inputs are connected together. The inputs of the NMOS and PMOS are connected together into this voltage input. So this will be the input, the two gates. And notice the drains of the transistors are also connected together, and that's going to be the output. Okay, then sort of going over, let's see, how do I move? I don't know. There we go. So this inverter is driving another inverter. Okay, so again, this is an inverter. We got PMOS and NMOS stacked up. The gates are connected together. The drains are connected together, and that makes the output here. So let me label a few of these things. I have to like keep remembering how this stuff works. So let's call this out one. And I label this guy. And I'm gonna do out two. Put that on here. Let's call this guy in one. Okay. So one inverter driving another inverter. Okay. So let me just start the sim and kick off. Again, there's like I don't know, maybe an hour-long tutorial that I put together from a couple of years back. That's also, there's a link so you can get some details. But let's say we simulate this. Oops. You guys probably cannot see my simulation window. So let me share that. It's gonna get tricky here. No, actually, let's see. I should be able to do this. Maybe this. Give me a second. Let me sort this out. Small. Okay, hopefully this is gonna work. Okay. All right. So guys, I'm hoping what you're seeing is a schematic on the bottom and some kind of a black waveform window on top.
Yes, we see.
Yeah, we see that.
Yeah. Okay. So I'm gonna go poke around this. So first I'm gonna look at in one, but you guys can see what I have there. By the way, I'm assuming has everybody used Spice before or heard of it or some level of Spice usage? Anybody not seen Spice? No.
Is it the same if we've seen P Spice but not LT?
Yeah, it should be. The engine is all the same.
Okay, yeah.
Yeah. So basically, this is the input. Okay, this waveform I'm showing you guys. And I created that in the form of a pulse voltage source. I'm going to pop that up. Hopefully you guys can see this voltage source little window. Basically, it says it's going from, this is creating a voltage that changes with time. So in the language of Spice, it's a transient voltage. Spice has three types of sort of signals or voltages. There's DC, that doesn't change. There's transient, which is versus time. And then there is frequency domain, or AC, which is changes with frequency. Okay. In this class, we pretty much always only use transient, maybe sometimes use DC. We don't really use AC analysis in this particular class. So we're usually looking for things that are changing versus time. Okay, so that corresponds to something like a pulse voltage source. The other thing that you can use is, it's actually, you almost maybe need to use it, not necessarily, but is so-called piecewise linear, PWL voltage sources. So you can then create kind of any voltage you want. But to start with, let's say we're looking at this pulse voltage and I got initial voltage 0, the on voltage. So when it goes on, it goes to 1.1 volts. Why did I pick 1.1? Because for this process, for this 45 nanometer process, the high supply voltage is 1.1 volts. So if I go look at, let me cancel this for a second. Pop over to, this is the Spice deck. So you see, I don't know if hopefully you guys see my cursor, but it says dot model NMOS, NMOS level 54, blah, 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 nominal VDD. So that's the highest voltage that the transistors, nominal means, so you can usually still go 10% above that, but so VDD nominally is 1.1 volts. That's why I put 1.1 volts on the drain of the PMOS. Okay, and the input is going from 0 to 1.1 volts. So in this circuit now, for this process, 1.1 volts corresponds to a logic 1, and ground, or 0 volts, corresponds to a logic 0. So again, if I'm looking at this pulse on the input, this is going from 0 to 1.1 volts, or if you want to think of this in the logic domain, it's going from 0 to 1 to 0 to 1, 0 to 1. Okay, because in the real world, we represent binary values with voltages. So a 0 corresponds to some voltage, a 1 corresponds to another voltage. In the world of CMOS, the 1 corresponds to your supply voltage and 0 corresponds to ground. It's not always the case for other logic families, but that's the case in CMOS. Okay, so we're going from 0 to 1, binary 0 to 1, 0 to 1, 0 to 1 on the input. Okay, so now if I plot the output, whoops, it's going, now the output is really mangled. And the reason it's mangled is because it's moving too fast. There's too much capacitance here. So let me adjust this capacitance. It's actually it was good that this happened. I put 1.5 picofarads here. Let me just make it what's a good number? 100 femtofarads. I'm gonna simulate. Okay, that's better. Okay, so the input is green. It's going from logic 0 to logic 1. And the output is doing what an inverter should do. It's going, so it's the blue. It's going from logic 1, which corresponds to 1.1 volts, to a logic 0, which corresponds to ground. Okay, so you guys see how this is an inverter? And then let me look at the blue is now the input for our second inverter. So if I plot the output for the second inverter, it's inverting the blue signal, right? So the blue signal goes low, the red signal goes high. So basically I'm going, this in 1 gets inverted at out 1, and out 1 gets inverted in out 2. So if I get rid of, let's see, what should I do? Get rid of out 1. Anyway, you guys get the idea here, right? So as you can see, there's lots of like really funky features here. There's this like bump here on the rising edges, here. You see that the output doesn't go immediately from 0 to 1 or 0 to 1.1 volt. There is a so-called rise time. There's a finite amount of time that it does that transition, and a finite amount of time that it goes from 0 to 1. That's called the fall time transition. There's a certain amount of delay. If you just look at the 50% point. So if I look at 0.5, whatever, 0.5 volts, there's a certain amount of delay from input to output. So the input's transitioning here from 0 to 1. The output transitions from to a 1 to a 0, a finite amount of time later. And we're gonna be digging into this stuff in great detail and doing analysis, okay? Right now, we're just looking at these transistors as if they're switches, and we don't worry about this right now, like there's rise fall times, and you can affect all these things by sizing your transistors and doing careful design. So in the project 1 description, I'm saying, don't worry about transistor sizing, etc. I just want to make sure, and also don't worry about the speed, okay? If you had this in milliseconds as opposed to nanoseconds, it's okay with me for project 1. Okay, just make sure that you get full transitions. Like if at when your output becomes stable, either at a 0 or 1, it should either be at 0 volts or 1.1 volts. If it's like stable at 800 millivolts, something really bad happened. Okay, something's not right with your simulation. You have to have proper logic levels on the outputs. Okay, it means that when the output gets stable, meaning at this point here or at this point here, it should be an appropriate 0, which is ground, or an appropriate 1, which is 1.1 volts. Okay, so, and I'm saying, well, prove that this is acting as an inverter. In this case, if I delete, can I just delete it? Yeah. In this point, this graph shows it, okay? So I have the input is going from 0 to 1, and the output is going from 1 to 0. So this graph is showing that this is logically acting as an inverter. Okay, this circuit over here. Any questions about that? About what you need to do on project 1? As far as the
Professor?
inverter is concerned. Yeah.
Yeah, the reason why you have a capacitor there to imitate like how it actually looks in real life, where you have rise times and fall times and stuff like that.
Yeah, so the capacitor is as we'll see several lectures from now, the metal lines. So not only are there transistors in the process, but there are also interconnections. So you got to connect these gates together. And those interconnections have parasitic capacitances typically, and parasitic resistance. Parasitic means something that's unwanted, that's just what it is. So if you had a line, which you always do, connecting two gates together, it's going to have some parasitic capacitance, and that's what's showing. That's 100 femtofarads. That's correct. Now, the other thing is, if I had this be, this is moving too far ahead. Again, we're going to get into all the gory details. If I made this really small, so I made it, so by the way, femto is 1 times, so f, small f, is 1 times 10 to the minus 15. So when I have 1 FF in SPICE, it's 1 times 10 to the minus 15 farads. Pico or P is 1 times 10 to the minus 12. Nano is 1 times 10 to the minus 9. And micro is 1 times 10 to the minus 6. So anyway, if I had this 1 femto, you might see this spike. I don't know if you see my cursor. These spikes on the blue, they might pop up even more. So let me do a simulation, see if that happens. Yeah, you see them, you see that got bumped up? These spikes. And we'll go into the gory details. This is not a real thing, because rarely do you end up with a 1 femtofarad capacitance. But that's why I went to 100 femto. And if this ends up being too big, let's say if I had picked like I did, say, let me do it slowly because so it'll become obvious to you guys what's going on. I'm gonna make it 500 femto. What you'll see is that the rise and fall times for the blue are gonna get longer and longer, okay? So simulated, you see that the rise fall times got really long because it's having a problem with the speed of operation given this capacitive load. And we'll go into these details again for this project 1. You know, basically you can deal with that by sizing these transistors, etc. But let me show you what's not acceptable, okay, for what you guys are doing. So if I made this 10 picofarads, which is 10 times 10 to minus 12, let's say this is my output. So what's going on with this output is, since the rise and fall times are longer than my bit period, the input never transitions correctly. So this inverter is not acting like an inverter. The input's going from 0 to 1. The output's just at sitting at different voltages. They're neither ones or nor zeros. And so this is an extremely like bad situation. Okay, so this is an example of like a failed simulation. Okay, it's not a failed simulation, but it's just something that doesn't quite work. Okay, everybody with me? So make sure, like, if for some reason, if you had 10 puffs for project 1 now, I could just say, look, I don't care if you guys do this. Say, okay, it's project 1. I'm gonna go to my, you know, for whatever reason, I just love large capacitances. I'm gonna keep that at 10 picofarad. Now I'm gonna slow way the heck down. I'm gonna make my period, my rise fall times are gonna, sorry, my on period is gonna be I don't know, 200 and 50 nanoseconds, and my pulse width is going to be 500 nanoseconds. Okay, and then I have to change correspondingly to my simulation time. I'm going to make that, I'm going to take that, make that 5 milliseconds. And I'm going to rerun this. Oops, that didn't work well. Hold on a second. What's going on? What did I do wrong? T period 500 nano. Oh, oops. So we had, let's see if that works. Not enough to debug. Okay, good. So I just had this being too long. Sorry, guys. Stop. No. Boy, can't stop it. Let me make this the. I'm gonna make it 0.1 milliseconds. See what that looks like. It'll still end up being too long. Well, I've jumped into milli, that's why. Micro. Sorry, my bad. Okay, now it's too short. -20 soon. Sorry, guys. It's helpful to be able to think. Okay, still too long. Okay, so you guys see what I did? That was like a lot of going back and forth. But because I had a very large capacitance, and that gave a very large rise and fall times, I got back to a working device by increasing my bit period. So now I'm like slowed way down, and this guy still acts like an inverter, except it's just much slower because it's driving a much bigger capacitance. And again, in the future, we'll see how all these things play, and how you design capacitance versus transistor size, etc. But just make sure your waveforms look like this on your outputs. They should be making full transitions going all the way from ground to supply voltage. So from 0 to binary 1, binary 0 to binary 1. Okay. Okay, so let's look around a couple of other things here while we're at it. So here in LT Spice, so this is a Spice deck. Okay, so again, I pulled this off for many classes. I was using a 180 nanometer TSM, so real process, 180 nanometer. Since it was so old, I was getting real device parameters, etc. I'm using it. This semester, I said, oh, that's getting kind of old. People are still using 45 nanometer. I mean, it's still in a lot of ASICs and stuff are using 45 nanometer. So I found this generic 45 nanometer process, Spice deck. So this is the model for the NMOS, whoops, up here. And then, whoops. And then the model for the PMOS. Where's the model for the PMOS? What? Where's the model for the PMOS? Here we go. I think it's just not showing up in this thing. So here's a model for the PMOS. Starts here and goes. Okay, so it's sitting here. You can change this stuff. I'd suggest you don't mess with this stuff at all. The transistor models. So what I was doing is I was changing this transient simulation time. I wasn't really using these parameters, and some of the stuff is left over. So really all you need is the transistor models and this dot trans statement. Okay, is really all you need. Okay, everybody good? Are we doing on time? 3, yeah, okay. So that was a little segue about project 1. So project 1, you do this for an inverter. You do it for a NAND 2, which is a 2-input NAND gate. And then you also do it for a NOR 2, which is a 2-input NOR gate. So hopefully from this simulation, you guys can see. So let me do this again. So you guys can see that what's going on here, going back to what I was describing. If you ignore this rise time, fall time, etc., you see when the input is 0 or ground. Okay, what happens when the input is ground? Or we can pretend like the PMOS is just a switch that is turned on, or it's a closed switch, and the NMOS is an open switch, and the output is just connected to VDD, to the supply. And indeed, you can see here, when the input is at ground, the output is seeing the full supply voltage, is seeing the entire 1.1 volts. It's not seeing 90% of it, whatever, because it looks like, to first order, this just looks like a closed switch. So it's not, there's no voltage drop across it or anything like that. It's putting the whole supply voltage here, okay? And vice versa, when the input is at VDD 1.1 volts or logic 1, whichever one you want to look at it, we can, our simple model for the time being, we can ignore all these weird rise and fall times and so on, and just pretend like the NMOS is a closed switch and the PMOS is an open switch. So here, the output is just connected to ground and it just gives you ground, okay? So not plus 100 millivolts or some value, intermediate value, there's no voltage drop across NMOS, you get the full ground on the output. Okay, so you get to go from 0 to VDD and vice versa. Okay, so that's what's happening. So let's now go back to our okay. Go back to my writings. So you guys should, are you guys seeing my iPad now or no?
I think still your desktop.
Yeah, desktop still.
There we go. Didn't hit that button. Okay, so that's what we got. So you guys kind of saw what I'm talking about. And then this is what an inverter looks like. Okay, so now let's talk about what a NAND looks like. Okay, so I'm going to talk about the NAND, and then I'm going to talk about the general case, and then we're going to go to NOR. Okay, so a NAND 2. This is the logical symbol for a NAND 2. And the, sorry. This is what the table looks like. Okay, so that's what it looks like. And now we implement this with our pretend switches by putting 2 NMOS in series. Okay, the bottom one is connected to ground. And I'm gonna put A here, B here. And then I'm gonna have 2 PMOS FETs. Let me just draw the PMOS. Make life a little. Draw the PMOS FETs in red. So notice the N MOSFETs are in series with each other. Let me draw the whole thing. B, A. Okay, so by this, I mean these two guys are connected together and this is connected to this. Okay, I'm not gonna draw that connection just because I'm just gonna make it a little, but you guys get the idea. So basically, look at the stuff. So first, let me tell you what this, look at how this, what this has in common with, let me copy the inverter over here. Yeah, for the sake of just right now, I'm not gonna worry about the substrate connection, but I'll bring it back in. So, okay, so let's look at what's going on here. So this was the inverter, this is the NAND gate. Okay, what do they have in common? Well, the PMOS is connected to supply on the inverter, and both of these PMOSFETs are connected to the supply. The NMOS is connected to ground. Here, one of the NMOSFETs is connected to the ground, but the other NMOS is between the output and the ground. Okay, so this one inverter is the NMOS is between the output and the ground. And we've kept that as the concept, which is the NMOS are always between the output and ground. And the PMOS are always between the output and supply. Okay, so you never see a PMOS down here between the output and ground, or an NMOS up here. So you always end up with a PMOS transistors, PMOS network between the supply and the output, and you always end up with an NMOS network between the output and ground. Okay, so that's what these two have in common. That's one of the things they have in common. The other thing they have in common is for every NMOS that's connected, it's got its gate connected to a signal, to an input. There's also a PMOS whose gate is connected to that input. So here we only had one input, and the N and the P, both gates were connected to that input. In the case of a NAND 2, we have two inputs. So we have one NMOS and one PMOS connected to one input, and one NMOS and one PMOS connected to the other input. So that's another thing they have in common, is the inputs are driving a pair of a PMOS NMOS pair, okay? And in both cases, the output is coming from the connection between this drain connection between the NMOS network and the PMOS network. Okay, so this is like common together. Okay, so let's get rid of this for a second and see how this goes. Okay, so now let's say A is, let's look at all these cases, right? Again, thinking about this as a switch. So A is, how do I do this? It's clean, okay. Up. So we got A, B, out. No, I don't want to do that. This. So A is 0, B is equal to 0. Okay, so if I have A0, B0, according to my model, my switch model, both of these PMOS switches have zeros on the inputs, means they're closed switches. Okay, so I can just draw those as closed switches. Okay, and then again, according to my model, both the NMOS switches are open switches. So that's out. So my output signal is connected to VDD. So out becomes VDD equals to 1.1 volt in our case, or equal to logic 1. Okay, so that's satisfies this case up here. Okay, so now let's say A is equal to 0, B is equal to 1. Okay, so now I'm looking at this point in the table. Here I have, if A is 0, B is 1, so B goes to this first switch. That means the switch, that PMOS is open. And then A goes to the second PMOS switch, it's closed. Okay, so B is 1, so that means the NMOS, the top NMOS switch is closed, and the bottom NMOS switch is open. Okay, slightly more complicated case, but not that complicated. So we have this switch is open, this PMOS switch is open, but this PMOS switch is in parallel with this switch, means that from a DC sense, it doesn't matter. The output is still shorted to the output. Sorry, the output is still shorted to the supply, to VDD. Okay, through this path. This path is not connected, but doesn't matter. I've already created a short. And then on the NMOS side, I've got one NMOS closed, but notice because the NMOSFETs are in series, this bottom NMOS being open means that I've cut out this path from the output to the ground. Okay, so I've just basically have a short from output to VDD and no path to ground. So just output again becomes VDD equal to 1.1 volts equal to binary 1. Okay, now this is exactly the same for A is equal to 1, B equal to 0. So I won't show that. We're just sort of switching which one of these guys is open, but the concept stays the same. As long as one of these two NMOSFETs that are in series are open, this is an open connection. And as long as one of these two in parallel is connected, this is a closed connection. Okay, so that covers these two guys. Now let's look at a case of A is equal to 1, B is equal to 1. So now my PMOSFETs are both open. And both NMOSFETs are closed. Okay, so in this case, out is shorted to ground equal to 0 volts or binary 0. Okay, which is this case. Any questions? No? Okay. So that's a very specific case. Okay. So let me first talk about a general case, and then I'm gonna come back. Well, let me describe it here. So notice, well, no, let me talk about the general case, and then I'll come back to the specific case. So in a general case of a CMOS, so this is what's called, to be specific, it's called static CMOS logic family. Okay, so why family? Family because, you know, you're gonna have inverters, NANDs, NORs, exclusive ORs, exclusive NORs, you name it. There's like a family of a logic, a logic family, okay? Now, CMOS is because you have NMOS and PMOS, and static, there are some other things you can do, some other logic type of gates you can make with CMOS that don't follow these rules, but they're usually called dynamic, that you can do pre-charge and this kind of stuff. You don't really see those very often, so I'm not gonna cover them. We're really only gonna pretty much cover static. I might just mention them here and there, but this is like 99.9% of the CMOS you'll see. Okay, so strictly speaking, it's static CMOS logic family, and it follows these rules. So now we're getting to the general. You always have a network of PMOSFETs. And that network is always sitting between the output and the supply. And you always have a network of NMOSFETs. And that network is always sitting between the output and the ground. Okay. And then the inputs. So I'm going to put a dash here to say it's a bus. Like you could have any number of inputs theoretically. It could be one input in the case of an inverter, two inputs in the case of a NAND gate, a NAND 2 gate, but you could have a 10 input NAND gate and you'd have 10 inputs, right? So that's would be the inputs. They go to both the PMOS network and the NMOS network, and they always connect to one NMOS and one PMOS. Okay, and you always have, obviously, because of the logic, you always only have one output, and it's this point connecting the PMOS network to the NMOS network. So going back to our NAND gate here, you see we have a NMOS network between the output and ground. We have a PMOS network between the output and VDD. We have two sets of inputs going to both P and N, P and N. Okay, so that's a pretty specific case of this general case. Okay, so here's the other generalities. Okay, so you always look at the logic functions. This gets a little complicated. Let's see. Yeah, we still have juices flowing. Okay, let's talk about the logic functions. Let's say you have two NMOSFETs in series. Okay, A and B. Do you guys see how this is makes an AND gate, A and B? So if A is high and B is high is the only way in connects to out. Okay, so the only way both of these are on, in connects to out. If A is low and B is high, you still don't get a connection between in and out. It's not really A and B, but it's sort of A and logic function. It's basically when they're A and B are both on, do you get this connectivity between in and out? I shouldn't say in and out. Let's call it C and D, I guess. I don't know. Okay, everybody with me?
Yes.
Okay, so now if you have two NMOS in parallel, it gives you an approximately, or not approximately, but it gives you a OR type connectivity. Because if A is high or B is high, you'll get a connection between the two nodes. Okay, C and D, that guy. Okay, so if they're in parallel, the NMOSFETs are in parallel, you get sort of an OR connectivity. If they're in series, you get kind of an AND connectivity. Okay, so, but look at the case of our, so NMOS network could either have NMOS transistors in series, or they could have them in parallel, or some combination. Okay, but in all cases, the C side is connected to ground, and the D side is connected to the output. Okay, so when A and B, so this is what it looks like. So general, like, so I'm gonna bring the same thing up here. So just looking at the PMOS case. So if I just look at this as in this context of a NAND, right? This guy connects to ground and this connects to output. Okay, so basically if A is high and B is high, output connects to ground. Okay, if either one of these guys is open, the output, basically this guy knocks itself out of contention and the PMOS network takes over. But for the sake of discussion right now, you get A, what is that, and B, right? But notice something here. Notice that if A is high and B is high, I'm passing 0 to the output. Okay, so it doesn't, although it's a and type of functionality, it's A has to be on and B has to be on. But when I meet that condition, I put a 0 on the output because I'm shorting the output to ground. So that's why you end up with A NAND B type of function. Okay, so that's why this ended up being a NAND gate here. Does that make sense? That gets a little confusing, I think, because, you know, I'm saying you have, because this is a generic way of coming up with a CMOS function, is you basically, you have an AND functionality, but because of the rules that we laid down, that we're making the NMOS network always connect to ground, we're always, when this logic meets the logic requirements, it actually passes as 0 to the output and it makes it bar, A and B bar. Any questions about that? So look at the corresponding case of an OR functionality. So if I have the N MOSFETs, connect it. And here is also OR functionality. So if A is connected, A is on, or B is on, I've connected this to the output. But in both cases, this is a ground. So I end up with A or B bar. Okay, so let's see, that was a chat question. Yes. So George is asking, is this the reason why CMOS is, it's easier to make NANDs or NORs instead of ANDs and ORs? And that's exactly the case. That's exactly the case. So notice it was really easy to make an inverter. We just needed 2 transistors to make an inverter. If you want to make a buffer, we'd have to put 2 inverters in series to get a buffer. So we need 4 times as many transistors to make a non-inverting buffer as an inverting buffer. And if we wanted to make a AND gate, we would have to take this guy and stick an inverter, so another 2 transistors in front of it and so on. Okay. So, okay. So now this is the other end of our the word complementary. All these things have double entendre in CMOS. Is we said CMOS has sort of 2 definitions, the complementary part of it. One of them refers to both P and N type transistors being available in the process, but there's also another meaning. The meaning is that, so first thing you do when you want to make something functionality is you think about the logic functionality in your NMOS network. Okay. And you put that together, whatever that logic functionality is, remembering that it will be inverted. Okay, so that's step one. So again, if I was gonna make a NAND gate, I'd say, okay, I wanna put A and B, and I know it's inverted, so it's a NAND, okay? So now, after you do that, you say, okay, I'm gonna have to make my PMOS network complementary to the NMOS network, which is the second meeting of complementary CMOS transistor logic. And what does that mean? That means if my NMOSFETs are in series, I'm gonna make my PMOS network be in parallel. And so A and B. And if my NMOSFET is in parallel, I'm gonna make my PMOS network be in series. So this is A, B, A, B. Okay, so this is the steps you go through deriving a particular logic function. You think about your logic function, remembering that it's going to be inverted. You use these rules for basically AND and ORs for the way you connect up NMOS transistors, in series for the ANDs and in parallel for the ORs. Okay, and then you connect this network to ground and the other step to the output. And then you go figure out the complement of this network and you put that on the PMOS. Okay. All right. So why don't you guys try an exercise, and I'm gonna threaten you guys to with your to pick one of you guys to help me with this. Why don't you guys think about how you would make a NAND 3? Okay, try that, put that together, and we'll take volunteers in about 5 minutes. Go ahead. Okay, guys, I lied. You only get 3 minutes. Okay, so do we have any volunteers to help me with this? Or tell us what you did?
I could go. It's Ethan.
Okay, thanks, Ethan.
I'm just thinking that we add another parallel PMOS to the NAND 2 and another series NMOS to the NAND 2.
Yeah, whoops, sorry, guys. Let me, it's killed my sharing again. Oh, am I still sharing? No, of course it killed it. So give me 1 second, let me, broadcasting. Sorry, Ethan. So you said add, so we had, this is the, so let me actually bring this down. Copy this over. So you're saying add another NMOS in series here,
Yes.
have a C input, and add another MOS here, which is exactly right.
Okay.
Beautiful, thanks. Okay, so now another 3 minutes. Take a shot at a NOR2. Go.
Professor, can you scroll up again really fast, please? Thank you.
Is this right there?
Yes, thank you.
Okay, sure. Okay, guys. Any volunteers?
Can I share my screen?
Sure. Oh, wait, I gotta let you do that. How do I do that? More. Wait. Where are you? Louis already told me how to enable everybody, but I forgot.
You just go to security
Security.
and then
There it is.
you click on
Click on.
it's like it should be like the third option after you click on security. It will say like enable share screen for participants.
Why don't I see that? Hold on a second. Now all of a sudden I don't see it. How to move chat, share screen, all present share. Oh, there it is. Yep. Sorry, you're right. Can you try Tree? Can you
Yes.
try that? Can you try sharing your screen now?
Oh, I cannot.
Hmm.
You need to stop sharing your side first so he could share his.
Got it. So I'm gonna. There you go. Hopefully.
You need to stop your sharing right now. So
Yeah, I thought I did.
I still see it.
Huh. Oh yeah.
I think you paused it.
What am I doing? This
You might be
will
on the
stop.
iPad.
Oh no. Oh yeah, you're right. Sorry guys. Duh. Try it now. There we go.
And this is what I draw.
Okay, looks right. Can you talk me through what you did?
Okay, so I have two PMOD in series on the top,
Mhm.
and then parallel in the bottom is for NMOS.
Mhm.
So for the truth table of NOR gate, when we have 00A and B00, the output is 1. So if A and B00 is going to be in a series, like that. The current go through and go out output, so we have VDD 1, so output is 1. And D2 open circuits, so it's going to be not connected. So,
Mhm.
and similarly, we can find out with 011011.
Right. Exactly. Okay. Awesome.
All right, thank you.
And any other thoughts? Nope. Okay, great. Thanks, Tree. So let me reshare again.
Professor, I had a super quick question.
Sure, go right ahead.
Is there a time where it's applicable to say VCC instead of VDD or vice versa? Or are they used interchangeably?
You're saying what's the difference between VCC and VDD?
Yes.
Okay, it's just a naming convention. So I don't know who comes up with this stuff, but the N-type or MOS type transistor, it's got drain, source, and gate. And then for whatever reason, for this one, they call the supply VDD. And I guess the VDD stands for drain or something. And then the bipolar transistor has collector, emitter, and base. So for whatever reason, they call the supply for bipolar transistors VCC. So they're both supplies, meaning they're like the high voltage, but the naming convention, for whatever reason, VCC is for bipolars typically, and VDD is usually for MOS transistors. Don't ask me why. Maybe when you have mixed and MOS or MOS and bipolars, we can separate them out. Did somebody have a comment? Brianna, did that answer your question?
Yes, it did. Thank you, Professor.
Okay, yeah. So in this class, you'll never see VCC or so in bipolar also, you'll see VEE as the lowest voltage. So you'll see VCC and VEE. So part of the reason you see VCC and VEE is because bipolar is used a lot in analog design. And a lot of times in analog design, at least at the board level, your amplifier might be connected between, say, I don't know, +5 volts and -5 volts. So this VEE may not be ground, right? It might be -5 volts or a minus voltage, and this VCC might be +5 volts, or it might be +3 and -3 or something. But anyway, that's why it's not ground, it's VEE. Okay, also in a bipolar technology or whatever, or circuit. And in generic CMOS, you'll see VDD and VSS for the lowest point, lowest supply. But because we're doing CMOS logic, this is always ground, always 0. So you'll just see ground and VDD in CMOS logic design. If you were doing CMOS analog design, you might see VDD and VSS. Okay. So any other questions, guys, about that? Okay, so with this methodology, okay, so with this methodology, as you'll see, like I think this is described in the lectures, etc., online, you can do sort of relatively complex logic. You're not limited with like NANDs and NORs. You could do some complex logic equation and do it sort of this step-by-step process where you're breaking it down into the NMOS network and then, you know, making those in series or parallel, and then putting the complement of that in the PMOS network and connecting the gates and bringing the output with the connection in between. But we're not, you know, in our projects and so on, no, I'm not gonna get, I think we're just gonna stick with like NANDs and NORs and inverters, maybe an exclusive OR or something like that. Okay, so that's how this static CMOS logic family works in terms of logical functionality. Okay, so let's look at what some of the things this brings us. Okay, so now I promised this, or I didn't promise it. This was created with the promise of this one because it's a low power. So what makes it low power? Let's think about it. Okay, so let's think about just a NAND gate. But whenever, you know, whenever I'm talking about a NAND gate or any kind of gate, as you can see in static CMOS, the gross functionality is similar. Or let me actually do an inverter. This is just so much simpler. Let's do an inverter. But you can see how a NAND gate like will theoretically work the same. Okay, so in VDD, in, out. Okay, so notice one of the sort of our requirements, or one of our rules for making CMOS logic, okay, is that the inputs go to the gate of NMOS or PMOS transistors. Okay, so this input goes to the gate, and my logic is always driving another logic function, right? So if you have, let's say I have this, let's say this inverter, whoops, this inverter is driving another inverter, maybe it's driving one input of a PMOS, and then, sorry, one input of a NAND gate, and an input of a 3-input NOR gate. I'm just making up stuff. And these inputs are coming from other places and all that stuff. But it's driving a bunch of stuff, right? It's driving a bunch of other CMOS gates. Okay, everybody with me? Okay, but the way we constructed all these CMOS gates is all their inputs are gates. They're all transistor gates. Okay, so what does that mean? It means that this guy, this NAND gate, is only ever driving capacitive loads. It's only ever seeing the gates of other transistors. Okay, so I don't know, I'm just gonna draw a bunch of gates about what this guy sees. And as you guys know, MOS transistors, their gates are purely capacitors. There's no resistive component in a gate. And I am never driving, almost never, sometimes it happens, say the drain of a transistor or a source of a transistor. I'm always only driving the gate of a transistor. Okay, so what does that do for me? So if I was going to add all these capacitances and pretend that they were linear capacitors, I'm only driving capacitive loads. Okay, so let's say that wasn't the case for a moment. Let's say I didn't have this rule that this logic function, that I was only driving gates and I was driving some resistive type of functions. Let's see what would happen. Well, let's say when my switch, let's say when my PMOS is on, let's say my in is 0. And let's say my NMOS would be open. And let's, for the sake of discussion, so this is not the case, right? Sake of discussion, let's say I was driving something that was resistive and not purely capacitive. Okay, what would happen is I would get a current, a continuous current floating from the supply to ground, okay, through this PMOS. So let's say I'm going from 0 to 1, 0 to 1, 0 to 1. Whenever my output is a 1, I would have DC current flowing through my gate. And remember, there's a lot of ways to look at power, but definitely one of the definitions of power is current times voltage. So if I say my voltage source is VDD, I would have a current, which was I would have a power that's whatever this current times VDD. And it would be flowing this whole time. In fact, if I had a 0 and then I went to maybe this this inverter isn't always switching, right? Sometimes the output stays high, sometimes the output stays low for a very long period of time. In fact, most of the transistors in your chip aren't doing anything in particular for very long periods of time. They're just sitting there either at a high level or a low level. And it means, what this would mean, that you would be doing power consumption the whole time this guy is at a high value. So even if this current, let's say this resistance was very large, right? And so this current would be very small. But if you're sitting there for a very long time, that current is flowing for that whole time. And remember, you have 20 billion, 20 times 10 to the 9 transistors in your chip. So if half of your transistors or a significant part of your transistors have this current flowing, this DC current flowing, all that stuff adds up to a big gargantuan number. Okay, now look at the case where the loads are purely capacitive. What happens? Well, when this guy shorts, let me draw that again. So when this guy when the input goes, whoops. So let's say my input goes from high to low. So what happens is I go from some point where the PMOS is off, NMOS is closed. So I'm going from this state to this state. Okay, it's on period. Okay, what happens? Well, initially, this guy was discharged to 0 volts because my input was 1 to this inverter, my output 0, and the NMOS would have shorted this capacitance to ground. Now let's say at t equal to t0, my input goes from a 0 to a 1. The PMOS switch opens up. The NMOS switch closes. This guy was initially at 0 volts. So what happens is current does flow and it starts charging up this capacitor. Okay, so current flows, charges up this capacitor, but when this capacitor voltage, its voltage goes from 0 to VDD. Once it reaches VDD, current stops flowing. Okay, because this guy is charged all the way up to VDD, okay, after a period of time. And at that point, it stops flowing. So as you guys saw, the output of my inverter does, has this rise time, fall time. Okay, so that's what the output looks like. So it's true that the gate is, during this whole rise time, what you're doing is you're charging up this capacitor with current from the VDD. So during this time, it's true, you're burning up current, you're using up current from the supply. But as soon as you get here, there is no more current in a purely capacitive load. The switch is closed, but this guy's already charged up all the way to VDD exactly. And so this gate can stay on forever. And during this whole time, once it gets to this point, there is no current flow. Okay, so for CMOS logic, there is no DC current flow. As I'm going to qualify this in some other, because there's like second and third order effects where there's leakage current and so on. But from a topological standpoint, there's no DC current flow. All the current flow happens in a CMOS gate is during the transitions from 0 to 1 and 1 to 0. Okay, so that is extremely powerful. Okay, because again, if you have 20 billion transistors in your circuit, in your chip, very few of those at any one time, let's say your chip is, you're using your cell phone to talk. At that point, you're really not like streaming video necessarily. You're not doing a whole bunch of other functions. So only mostly sort of the audio channel in that cell phone chip is working. Or if you're watching streaming video, you're not, necessarily playing a video game or what other type of functions. So at any one point, only a small part of the chip of those 20, 30 billion, 10 billion transistors are transitioning between 0 and 1. Most of the other transistors are just sitting there with whatever state they had before. Okay, so the average power consumption of the chip can be made quite low in a CMOS logic. Okay, and that's why if you're doing a bunch of stuff on your computer simultaneously or a bunch of stuff on your cell phone simultaneously, the battery tends to drain faster, because what you're doing is there's more active circuits, more transistors are switching between 1 and 0. And so that's when the power consumption happens. Okay, guys, there's a couple of other features, but I'm gonna stop here because we're out of time. Any questions?
So the project is due next Friday, right?
Yeah, unless you guys complain, and in which case it can be due later than that.
And how are we turning that in? Is that
Email
through
it.
Canvas or?
Yeah,
Okay.
just email it. Yeah.
And just to make sure we're going to be doing the presentation in class, right?
Yeah, and like it's kind of like how we're flowing. We're just gonna. You're talking about the project.
Yes.
Yeah. So no, the project, just turn it into me. The presentation will be the update to your presentation, which is the chip comparison.
I'm sorry. Actually, I was talking about the presentation. That's
Yeah,
not the
yeah,
project.
yeah. So we'll do it in class, and we just kind of like pop up a few different ones. We might not do all of them. Maybe we'll just take, because it might be some. Again, I'm using that as a way for us to learn. So we'll just pop up a few here and there, or if somebody wants to volunteer, and then we'll sort of dig in. So each one of those discussions might take up, I'm not gonna limit the time if I feel we're learning. So it won't be like, hey, 2 minutes, 2 minutes, 2 minutes. We might get stuck on one thing, but let's be ready to like talk about your presentation. Does that answer your question?
Yes. Thank you.
Okay, sure. Anything else?
Professor, just a quick question.
Uh-huh.
Is a project, do we do it with our groups or each one individual?
You do it each one individually.
Okay, thank you.
Yeah. I mean, feel free to talk about it with each other. I don't have a problem with that. But like, I think everybody knows what's in, what's out. But it's not a group project, but I'm very happy for you guys to get help from each other and so on. That's perfectly kosher.
I have a question, Professor,
Yeah,
if that's okay.
sure.
Could you please upload this lecture?
Sure. Be happy to do that.
Thank you.
Sure.
All right. Thank you, Professor. Have a great weekend.
Okay. Thanks, guys. Take care.
Thank you,
See
Professor.
you.
Looking forward to seeing all you guys next week.
Professor